Imagine this. It's 3:11 a.m. in Geneva. A cryostat pings, a decoder spikes, then silence. Not failure, stability. An ML brain just caught a burst of quantum hiccups and stitched them shut before the coffee finishes dripping. A circuit that face-planted last year lands clean. Slack explodes. Headlines whisper, fault tolerance isn't theory anymore, it's plumbing. Guys, welcome back to Quantum-Fi, the show where physics, code, and finance collide at light speed. Today's mission: major quantum developments in 2025. What actually moved the needle? No recycled hype, no vendor bingo. We'll trace the breakthroughs, unpack why they matter, and hand you a playbook you can actually use. Grab your beverage of choice, silence the pager, and let's get started. 1. The system flip. Why 2025 was different. For a decade, demos asked, can a qubit survive? This year, the question changed, can the whole system behave? 3 drivers made the pivot real. Error correction crossed the line. Grow the code, the logical error shrinks. Below threshold territory, finally. Reflexes got fast. Transformer-style decoders read syndromes in tens of microseconds and trigger the right fix before phase wanders off. Control got smart. Reinforcement learners sculpt microwave pulses and entangling gates, 2-qubit drama shortens, uptime climbs. Takeaway: reliability stopped being a slide and became a service level. 2. Fault tolerance and control. The engine room. Surface codes alive and kicking. Logical beats physical as distance rises. That's the whole game. More checks, fewer oopsies, longer coherence in practice, not just on a whiteboard. Decoders with reflexes. Think of them as an immune system. Syndrome bits stampede in, a neural net predicts the culprit and flips the right patch in microseconds. Latency isn't a nice to have, it's the difference between kept superposed and oops measurement. Throughput or bust. A serious machine spews data like a fire hose. We're talking 100 terabyte per second decoding pipelines, cryo-friendly electronics, and compilers that plan around feedback deadlines. AI-tuned control. Overnight training runs teach qubits kung fu. Error rates drop, gates tighten, runtimes shrink. Less time in the blast radius means fewer scars on the wave function. Bosonic and cat tricks. Hardware-level protection buys you smaller overhead. Fewer physical per logical qubit when the cat stays coherent. Distillation at logic level. Neutral atom teams pulled off magic state distillation with logical qubits. Translation: the door to universal, fault-tolerant computing creaked open. Takeaway: QEC isn't a keynote, it's a heartbeat loop. Sense, decode, correct, humming under real workloads. Hardware reality. Who did what? Why you care. Superconducting, Google and IBM and friends. Threshold hugging experiments. Faster 2-qubit gates. Nightly autocal. Deeper circuits that end without tantrums. System 2 lands next to a supercomputer because hybrids are the new normal. Trade-offs: surface code overhead is still a dragon. Materials uniformity sets the ceiling. Trapped ions. Ion Q. Quantanium. Prototype. 2-qubit fidelities past 99.9%. Clean error models. Machines you can rent without a forklift. Marathoner energy. Slower gates but steady stride. Trade-offs: scaling wants modular controls and photonic links. Or you drown in cables. Neutral atoms. Q-era plus consortia. Big tweezer arrays with flexible connectivity, repeated error cycles, ML decoders in the loop. Logical level distillation was the mic drop. Trade-offs: array stability and crosstalk keep engineers humble. Photonics. Xanadu, Psi-quantum. Modular networked ambitions, multi-chip, rack-style builds on silicon photonics. Manufacturing loves this story. Trade-offs: loss, indistinguishable sources, and integrated detectors write the difficulty curve. Topological. Majorana. Exotic quasi-particles in designer nanowires promise hedgehog qubits that protect themselves. Trade-offs: replication, scaling physics, and braiding overhead are the boss fights. Annealing, D-Wave. A useful problem supremacy claim on materials simulation turned heads. Trade-offs: model-specific wins don't magically transfer to gate model advantage. Takeaway: no single champion. Fit, manufacturability, and QEC overhead decide who shines where. Up the stack. The software finally grew teeth. CUDA Q, stitching kernels to GPUs. Python-first emulators letting teams dry run fault-tolerant circuits, and a whisper-turning real decoder as a service. Rent the antibodies. Keep your rigs simple. We'll go there next. After the break, cloud details. 4. Cloud, tools, and ops, where the work actually happens. Let's float up the stack. CUDA Q glued quantum kernels to GPU muscle, so you prototype, simulate, schedule, and post-process without juggling 5 toolchains. Python-native DSLs and high-fidelity emulators made fault-tolerant circuits and surface code flows debuggable before you burn precious device shots. And the spiciest rumor turned pilot, decoder as a service. Stream your syndromes to a cloud immune system, get back corrections in real time. Don't build the antibodies, rent them. Takeaway: the developer experience finally respects your time. Cryo to cloud, one pipeline, fewer brittle hacks. Applications: beyond benchmarks into utility. Chemistry and materials inched forward. Phase estimation and VQE variance, tighter error mitigation, and annealing win-on-spin system simulation that actually matters to condensed matter folks. Power grid optimization stopped LARPing and ran hybrid unit commitment on real datasets. Quantum for the gnarly kernel, GPUs for the rest. ML times quantum grew up in 2 directions: AI managing calibration, pulses, and decoders, and tiny quantum subcircuits acting as exotic feature maps inside classical models. Verification and certification sharpened up too, with device-independent randomness moving from bar trick to audited artifact. Runtime reality check. NISQ stays noisy. The action is hybrid now. Fully fault-tolerant apps arrive narrow first, chemistry primitives, crypto sandboxes, then widen. Policy, standards, and people. The boring that moves mountains. PQC hardened. 2024's finalists locked in, and a backup KEM joined the roster. Translation: your migration clock is now ticking in production, not in slides. The EU's 2025 strategy braided Euro, HPC, and Quantum into one roadmap, and the UN's International Year of Quantum turned awareness into budget lines, internships, and national programs. Workforce: the gap is real. Controls, cryo, compilers, and a brand new job title, QEC operations. Universities finally flipped labs from tour to hands-on. Takeaway: security and talent are now schedule items, not vibes. Timelines: what to watch next. 0 to 12 months, bigger code distances, decoder in the loop cloud pilots, more than 100 qubit developer boxes, neutral atom logic scale-ups, photonic module chaining. 12 to 36 months, first narrow FT applications, enterprise PQC rollouts, early topological replication results, annealing broadens critical workloads. 36 to 72 months, practical FT chemistry, crypto-relevant demos and sandboxes, hybrid HPC plus QC production pipelines with SLAs and dashboards. Playbooks: Monday morning moves. Builders: design hybrid from day one. Automate calibration, log syndrome, telemetry, prototype in emulators, and treat decoder latency as a P0 metric. Enterprises: start PQC inventory now. Pilot crypto agility and earmark 1 to 3% R&D for quantum. Co-locate with HPC where possible. Rent hardware via cloud. Researchers: shave T-count and depth, build mitigation that composes with QEC, publish latency numbers, and cross-train controls plus ML. Investors: fund manufacturability, materials, decoder throughput, and cloud integration, not vanity qubit counts. Track policy tailwinds as demand catalysts. Challenges: non-negotiables. Error budgets: push 2-qubit fidelity and shorten circuits. Throughput, syndrome, bandwidth, and real-time feedback at scale. Materials: Uniform junctions, low-loss photonics, cleaner traps and tweezers. Systems, cryo, I or O density, control electronics, vibration, and EMI. Algorithms, FT-ready workflows with economic wins. Interop, IRs, compilers, pulse formats, and APIs that actually talk. Talent, 24/7 QEC ops, staff the heartbeat. Scenarios, Doom, Default, and Upside. A. Crypto Crunch, low probability. A quiet FT leap enables targeted key forgery demos, markets jolt, PQC lag gets exposed. B. Steady hybridization, most likely. Hybrids deliver ROI, narrow FT apps land, PQC migration completes on schedule. C. Quantum flywheel, the upside. AI for QEC plus FT chemistry trigger materials and battery step changes. Cost curves slide fast. 2025 flipped quantum from fragile demos to integrated systems. QEC plus AI control plus manufacturable hardware plus hybrid software. That's the winning vector. Smash that like button if this tightened your roadmap. Drop a comment. Which platform hits the first real fault-tolerant application? Superconducting ions, neutral atoms, photonics, or topological? And why? And hit subscribe to stay quantified. Next episode, we'll unpack PQC in practice, migration playbooks, pitfalls, and how to crypto-proof your stack before the auditors do. Until then, keep your curiosity high, your qubits cool, and your decoders caffeinated. Quantify, signing off.